So while you're watching this, you want to make sure that you are listening carefully. I'm going to pop in with some questions every once in a while. You want to participate. And if you pay attention and you understand what we're doing today, then the assignment is going to be a piece of cake. Okay. I'm essentially going to explain everything that you need to know and even give you a practice chance to practice the assignment during this class so that you feel really confident about your answer in the assignment. Okay. All right. So how do seismologists figure out exactly where the epicenter is? In other words, how do scientists know where the heck that earthquake occurred, right? Like, first of all, I mean, we know where the earthquake occurred, right? Like there's a ton of damage, right? There was an earthquake in LA. Yeah, so it was in LA, but they always say, like, they'll be like, it was centered 5.2 miles southeast of Los Angeles at this latitude and longitude. What? Like, how do they know that? How do they figure that out? That's science. And so that's what you're going to learn today. And on Thursday and Friday, you are going to do a lab where you actually figure that out. You do the science to pinpoint the locations of some actual earthquakes and their epicenters. All right. So this is your chance to understand the science behind it. And then Thursday and Friday, you're going to do it yourself. All right. Okay. So here we go. First of all, seismologist. Seismo means, can you guys see this? Yes, you can. Good. Seismo, that term seismo, the root word seismo, means earthquake. So seism means earthquake. It's actually from a Greek word, seismos, which means to shake. Okay, and so that's where that word comes from. So seismologists, seismic station, seismic waves, seismograph. You're going to hear that a lot, and that's where that word comes from. So size is how we say that. So it kind of looks like this word, size. It sounds like that word, size. Okay, that's how I think of that. So seismologists are people who study earthquakes, and they need three things. They need data from a seismic station. They need a large map, and they need a tool to draw perfect circles. So we're going to go through how they use each of those things to figure out where earthquakes are. So number one, a seismic station. Let me go back. A seismic station is just a place. It's a location that has seismic equipment, like earthquake equipment in it. And this is a picture of one. This is the William Spain Seismic Observatory at Fordham in the Bronx. So if you live near Fordham or you live in the Bronx somewhere, there's one really close to you. There's also one at Columbia University. NYU has one. There are colleges out in Brooklyn and Queens. Queens College has one. I think York College has one. So these are all over the place. They're tiny little buildings like that one on the left. They don't look like they have anything in them, but they go down to the basement. This one's like 30 feet underground. And this is what it looks like on the right. Kind of gross, right? It's like, what is happening in that room? It's just a bunch of equipment, a bunch of wires, and it's all hooked up to record seismic waves, this energy that's released by earthquakes. And what they have in there are these things called a seismograph. So this picture is a picture of a seismograph. It is essentially a big, like a roll of paper. They call it a drum, and it rolls around, and there's this needle right here that shakes. And it normally shakes a little bit because there's background shaking of the earth. And then when an earthquake wave comes in, energy from an earthquake that happens somewhere on the planet, that little needle shakes. I'm sure that this is not news to you. Hopefully you have heard this before. And that seismic station, there are seismic stations all over the earth, like I said. So if an earthquake happens here, the energy can shake and get to that seismic station on the surface, but it can also go into the earth, and it can make its way to a lot of different stations all over the world. And so seismologists will use that information. So I wanted to share with you guys this is a live version of a drum. I don't know if any earthquakes are happening around the world right now, but if they are, And if this seismogram or seismograph picks it up, we might be able to see it. This one's in Lincoln, Nebraska. And it doesn't look like anything's happening here. But you can see that in the past, there have been some shaking, right? Where some seismic waves have been recorded on this seismograph up here and down here. Let's see, I'm going to show you another one. Since nothing's happened on this one, I'll show you this one, because this one you can see it happening. So here it is, background shaking of the planet happening. But then as soon as the seismic waves come in, ooh, look at that little needle moving. There it goes. So that's what happens when a seismic wave comes in, right? And it, like I said, it can come in from all over the planet. It doesn't have to be like right next door. But if you have a seismic wave come in, that energy given off by the earthquakes help scientists to figure out where the earthquakes are. And there are two basic types of waves that help them. One is called a primary wave and one is called a secondary wave. We abbreviate it by calling it a P wave and an S wave because that's what they start with. And the reason we call them primary and secondary, primary waves arrive first. They get there first, so we call them primary waves. I remember that with a weird way. I'm like, oh, it begins with a P, so first P waves. I know that's corny, but that's okay. And the reason they get there first is because they really travel fast. So they leave the earthquake and they start moving outward from that earthquake. And so the seismic stations get them first because they're traveling the fastest, okay? And you can see over here, this is a seismogram that records that information on that roll of paper. So here's the P wave that arrived first, and here's the S wave that arrived second. So S waves, we call them secondary waves because they arrive second because they travel slower, okay? And those are actually waves that travel so fast that they move through the earth faster than the actual shaking that you feel afterwards. The surface waves, the stuff that actually causes the damage, are slower than the slowest S waves. That arrives afterwards. So interesting that cats, dogs, animals, they can actually, scientists think they can pick up on these P waves and S waves, that they can sense those P waves and S waves. So if you've ever seen a video where an animal starts freaking out and then all of a sudden there's an earthquake, we might be able to use animals to help us try to predict earthquakes in the future. There are actually people who are working on that right now, scientists who are working on that, which I think is interesting. So, question for you, what wave is arriving right here? What type of wave is arriving right there? You can type it in the chat. Is that a P wave, or is that an S wave, or is that a surface wave? P wave, S wave, or a surface wave? You can type your answer in the chat where I put that red arrow there. Is that a P wave, an S wave, or a surface wave? I see lots of right answers. If you said P wave, you were correct. So how did you know that that was a P wave? Does anybody want to unmute themselves? Raise your hand and let us know. How did you know that was a P wave? Lots of people got it right. Nobody? Everybody's shy because I'm recording. Batu, yes, because it's the first wave that arrived. Nice job. So that is our P wave because it's the first one that arrived. This one right here, these are the second ones to arrive. That's when it shook a little bit more. And you can even see that the secondary waves are probably stronger. That's making the needle shake a little bit more. And then the surface waves don't even show up on here. They're like way off to the right. They show up much, much, much later. Okay, nice job, you guys. So the most important part that they can get out of this is that they can actually use this to find out the distance to the epicenter. In other words, they can tell how far away the earthquake is. And the way they do that, I don't know if you guys can see, the P and the S wave are a certain, they arrive at a certain time. There's like a lag time between the P wave and the S wave, right? So that difference is what they look at. If it's far, if they arrive very long after one another, it means that the earthquake is farther away from that earthquake seismic station. Whereas here, these two arrived a little bit closer together, right? So because those two, there's not a big difference in time between when they arrive, then that earthquake was probably closer to this earthquake episode or to this seismic station. So that's one of the ways that they can tell. Farther away, then the greater the time difference, then the greater the actual distance from the earthquake, okay? So what can scientists learn about an earthquake from seismic wave data at a seismic station? What can they find out? What is the ultimate thing that they find out? You can type your answer in the chat. It's really one thing, the one thing that they find out. Uh-oh. Is everybody typing? You're typing a lot. What can scientists find out? What is the one thing that they find out once they look at that seismic data?
Wait, Miss Lehnert.
Yes, sir.
Are you recording?
Yes, sir. That's all he wanted to know.
No, because I thought I was screen recording because it said recording in the top corner.
Yeah, yeah. Lots of answers coming in. Nice. Yes. How far away it is. It's the difference where it travels. Yeah. Yeah. It can also tell you how strong the waves are. Yeah. Nice. So the main thing that we're looking for is that it's the distance, right? So it can tell you how far away that earthquake is. Okay. All right. So now that we've got that, we've just figured out this one, right? The data from the seismic station to tell us how far away it is. The other two things that scientists need are a large map and a tool to draw perfect circles, okay? You guys have probably used those before. You guys ever seen those like compass? It's called a compass. I think that's what it's called, right? Where you can like, you put the little like needle here and there's a pencil and you spin it around. That's the kind of tool that they have to use, all right? Yes, yes, I see lots of yeses, nice. So large map. All right, so what do they need a large map for? Well, let's say, let's use that color today. Let's say that there's an earthquake that happened somewhere, and we know that because here in New York City, which is right there, that's New York City, we have a seismic station, and suddenly the needle starts moving, and we know, we're like, oh, there's an earthquake somewhere. Hopefully everyone's okay. But very exciting for a seismologist because now they can start analyzing the data, right? So they use their seismic data, they get their P and their S waves, and they analyze that and they figure out, ooh, this earthquake was 1,000 miles away. Okay, great. So they're like, okay, so it's 1,000 miles away. But what they don't know is like, is it 1,000 miles that way? Or is it 1,000 miles that way? Or that way, or that way, or that way? Like they don't know what direction the earthquake was in. Like they have no idea. All they know is that it's 1,000 miles away from New York City based on that seismic data. And you might think to yourself, well, that's dumb. Why don't they make a better system that can like tell them where it is? It just doesn't exist. Like right now, we just don't have that technology. So what they do is they say, okay, I know that it's 1,000 miles away from New York City. What if I draw a circle that has a radius of that distance? And now I know that the earthquake happened somewhere on that circle, right? Which is great, I guess, but still not that helpful, right? Because you could be like, well, I know the earthquake took place like, I don't know, somewhere out in Arkansas, but that's still a lot of places along Arkansas, right? I need to pinpoint it. Like that's the job of a seismologist, to let everyone know, here's exactly where that earthquake took place so that other people can go to that location and start studying it. Okay, so what do they do next? Well, this is where they got to get on the phone. They get on the phone, they go bling, 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 bling. I sound like an old-timey person, don't I? And they say, North Dakota, did you guys get those seismic waves at your seismic station? And they say, yeah, we did. And they say, well, how far away was the earthquake from you? And they say, ooh, it was only 700 miles. So here's North Dakota. They're up there and they're like, oh, okay. So now people in North Dakota, and they're like 700 miles away, let's draw the circle around North Dakota and figure out how far away it was from North Dakota. Aha. Now we know that the earthquake had to be somewhere on this circle, 700 miles away from North Dakota, and it had to be on this circle here, 1,000 miles away from New York City. So either that earthquake took place right here where they cross, or right here where they cross. Well, how are they going to figure out which one it is? Did you figure it out yet? You got to call another station. So let's say they call somebody else up. They call somebody in Denver, Colorado. Call them up. They say, oh, yep, we got those seismic waves. They're 1,100 miles away. Draw the circle. And now we know that the earthquake had to have taken place where all of those circles intersect. So where do all three circles intersect? If you guessed here, you were correct. That is the location of the earthquake epicenter. That's where that earthquake took place. But you can't do it with just one seismic station. You've got to have all three, at least three. You could have more than 3 seismic stations. It would just like, they would all intersect at that one location, but you have to have at least 3. If you have only one station, all that tells you is that that earthquake had to take place somewhere on the circle at that distance away from the epicenter. That doesn't tell you anything. And sure, you could use 2 stations, but now you've only narrowed it down to 2 locations where those 2 circles intersect. You gotta have 3 stations so that you can figure out where all 3 circles intersect to pinpoint it. It's called triangulation. And it's something that your phones use every second of the day to tell you where you're at. It locks onto 3 different satellites, and that satellite knows that you're a certain distance away, and that satellite knows you're a certain distance away, and that satellite knows you're a certain distance away. It draws 3 circles and pinpoints you exactly the way this works as well. Pretty cool, huh? That's dope. I agree. So what I want you guys to think about right now is, how would you describe this process to a family member or a friend, like a younger brother or sister or a friend? Like, how would you describe how scientists can do this? And we're going to do this. This is going to be like a practice before you do your actual assignment in Canvas. This is going to be like a little practice that you're going to do on something called Padlet. I don't know if you guys have ever used Padlet before. So I'm going to stop recording because we don't need to record this part anymore.